Okay. So in the first two lectures, I tried to explain a certain point of view on integrable systems. And I stressed several times that if you're simple-minded and you want just to solve, you have nonlinear system you want to solve, you can solve it without even mentioning a word Hamiltonian systems. You just made a spectral transform, you establish a certain analytic property of common eigenvector of two linear problems, and from these analytic properties you can uniquely define this vector and at the end solve the Cauchy problem for your system. It's a subject of additional series of lectures to go step by step how it works. Just at the end there are some explicit formulas involving theta functions. I give just one example of them. Getting these formulas is not a point of my goal of my last lecture. Namely, what I would like to explain in the remaining time is why all these systems that came just as a vector field defined by Lax equation, why they are Hamiltonian, and why and what we can get for the Hamiltonian interpretation of this equation from the algebraic-geometrical point of view. Namely, how to construct actually angle action variable for this system, how explicitly write. So, and at the end what I am planning to do is I want to make a connection with the previous talk by Rishetikhin and say that I'm actually going to define by these formulas I'm going to write a very explicit form on G cross G, which was said has nothing natural on it. So what I'm talking about, we just in a very general, more or less senseless form, defined the equations of our interest and as certain flows on a space of L's, space of operators. They're defined by Lax equations. All of these Lax equations, by Lax equation, I'm using here only L, and the particular form of the equation depends on the choice. What is the class of operators? Is finite dimensional matrix, some sections of some bundles of algebraic curve, or differential operators in one or two variables. Doesn't matter. They all have the same definition. So I want to give on the same level of generality the answer. Why this equation are Hamiltonian? So what does Hamiltonian means? To begin with, we should on our space to define a symplectic form. So I'm going to introduce a certain two form on a space of L's which turns out to be symplectic with respect to this form. All these last equations are Hamiltonian. So I want to begin with definition of some two form on a space of L. So there is not so much I can use. I want to use the same collection of letters. So on a space of L, how you can write the most natural way a form. Two form. Okay, let's try to write something. I'm trying, it's not mathematical approach, but what I'm saying is the only form you can write in terms of L's. So, what is L? L is a matrix, L of Z. So, matrix entries are functions on our space. So, delta L is one form, matrix valued one form on a space. So if Lij of Z are functions, this is a matrix valued one form whose entries are basic one forms on our space. I write delta instead of D, its external derivative, because later on I will have differential in Z. So just to distinguish, this is external derivative of L on our space. So this is one form, matrix valued. What else we have on L's? Okay, we already saw. This is, if you have eigenvectors, I form a matrix of eigenvectors. So K is a diagonal matrix. Kij is Ki delta Ij. So this is the collection of all eigenvectors of my L operator. In this form, this equation defines psi as a function of L. So it's a function on our space, matrix valued function. Okay? So together with the matrix comes a collection of its eigenvectors. So let's take delta psi, external derivative of this function. So it's another one form on our space. To make it independent on the choice of ordering of these eigenvectors, let me just define the following expression. So, that is going to be, this is two form on a space of L's. This is wedge product of two one forms. Taking the trace, I made it scalar valued two form on a space of on a space of L's. What I'm trying to explain now is that in the same type of generality as Lie constant, Kirillov, Berezin form on a space of Lie algebra, there is a form on a space of operators. The only difference now, we have extra, we have a z-dependent. So this is a scalar form, two form on our space. It depends on z, on a spectral parameter. we should erase this z dependence. How you can erase z dependence? Take a sum of residues. That's all, nothing. This is all what you have in your disposal. dz omega minus 1/2. This doesn't matter. Sum of all omega is minus 1/2. Sum for all poles of L. The residue dz. This is two form. I'm not claiming it is closed, it is non-degenerate. It's just the only form you can write on a space of operators. At least I was unable to imagine anything simpler and more natural than this one. Yes? It's gauging version. There are many reasons, but this is the more or less the only thing that you can write having just L at your disposal. I want to write on a space of L's a form. This is the simplest you can imagine. Sorry? You wrote 1/z? 1/2. For some reason, you may forget. So I'm taking the residue over this expression. It's two form. In fact, there are, and later I'll explain that, it turns out that in all integrable systems, your Lax equations are Hamiltonian with respect to this form. And it serves for zero-dimensional, finite-dimensional system, KdV, Kp, sine-Gordon, whatever. Everything is having this representation. Actually, I am cheating a little bit because having a matrix, you can think or look at a matrix in two different ways. One way is linear. You can think about matrix as an element of Lie algebra. Or you can think about group. In both cases, there is, if you treat L as an element of group, there is a simple modification you can imagine. You write trace psi inverse L inverse delta L, delta psi, dz, sum of residues, the same. So this is just two ways of looking on a matrix. It turns out that the same equations are Hamiltonian with respect to both of them. And this is the nature, and one is a linear form, the other is quadratic form. So this is the same equation are Hamiltonian with respect, this is observation that go, not this, but the observation that KdV is Hamiltonian with respect to two brackets. It goes back to Franco-Magri. But actually, it's a way, the presence of two symplectic forms is, you can treat operator in two different ways, as element of group or element of Lie algebra. Okay, so this is the form. In a second, I'll give you example how you computed what is this form. But, okay, but it's not exactly what I am looking for. It's not a form on a space of L's. The reason because psi is a function of L, but actually it depends on the normalization. So it's not only on the space of L's, but on the space of some extra data you need to fix in order to be able to write such a formula. So can we just see when this form is so when omega is normalization independent, or in other words, omega is when omega is well defined on the space of L's. Because at this moment, without understanding how it depends on the normalization, we still have a form written on a space of L's plus a space of possible normalization. Yes?
You said that you make it independent of normalization, they put something.
Yeah, not exactly, no. It's independent on the ordering. You see, psi is a matrix of eigenvectors. So I don't know how to order them. To erase this, I put psi inverse, but it doesn't kill. You will see in a minute how the normalization. Okay, so what is normalization? Change of normalization. So change of normalization, you just transform. What is normalization? You multiply a vector by a number. So it is multiplication by h of z. H z is diagonal matrix. So this is the transformation corresponding to change of normalization. Use this here. What you will get? You will get psi inverse delta L psi wedge delta H. This is the additional term you acquire. Sum of residues dz. Okay, just delta psi comes. So when you psi times H inverse, you just compute delta H inverse dz. This is the transformation. Psi acquire under this transformation the additional term. Everyone, just from the original equation, you know that psi inverse delta L psi, it's the same as delta K as a variation of eigenvalue. You can easily compute. Okay, you have the equation L psi equal psi K, take variation and use this identity. You get that this term actually, it's a homework exercise, this form, yes?
Is there a trace before or after the sum of the residues?
Sure. So all what you get this additional term is the following. It's delta K dz wedge delta H trace sum of residues. So this is omega goes to omega plus this additional term under gauge transformation. And H is an arbitrary function. So when omega doesn't depend on the normalization. Only omega is independent on normalization when delta k dz is regular at poles of L. So when there is no pole here, you don't get anything from the residues. This simple fact. Okay, let's see what this simple fact tells us. Let's take the example. L of z is u naught plus sum of ui z minus zi. This is our example, the first example. K is an eigenvector, eigenvalue of L. K has poles where? K, the eigenvalue of this metric, has poles at points zi. So near zi, it is nu I, z minus zi plus so on. So what the condition that delta k dz is regular says? It says that delta nu I equals 0. So the residue of the eigenvalue is a constant. But what are these residues? What is the residue of k? They are eigenvalues of ui. So our space of L, and what are points of ui with fixed eigenvalues? It's an orbit of the adjoint action. So in this example, we see that in order this omega to be well defined, we have to choose ui in orbits of the adjoint action. So the form by itself defines you symplectic leaves. So in fact, this form that I'm writing, I didn't say that it's symplectic. It's not symplectic. It's always degenerate in the same way as a canonical Lie, Cost, and so on form becomes non-degenerate and good defined only on orbits of adjoint action. But again, this condition and this, or the goal to define the form in an invariant way describes symplectic leaves. They become well-defined only after being restricted on a certain subspaces of our space. So our space is not symplectic, but later it turns out it is Poisson manifold. But you can find the leaves from the condition that this form has to be defined in a natural way. Okay. I'm going to do some simple computation in order to show equation, Lux equation, L dot equals commutator AL, where A is V Z minus mu, L the same as before in our example, and V is chosen to be L to the power K of mu. So this is the Lux equation. So Lux equation is Hamiltonian with respect to omega. And actually, along the way of proving this, I'm going to compute the Hamiltonian. I'm going to find in a way, not only, okay, the two form I gave, but why the Hamiltonian? It's very simple. So, okay, forget about, at this moment, I'm not going to prove that this form is non-degenerate or closed. Let's prove the following identity. What is the definition of Hamiltonian vector field? You have two forms, you contract it with a vector field, and that has to be a full one form or full differential of some function. This is the definition of the Hamiltonian vector field. What I'm going to check, very simple, is that if I plug in vector field defined by Lux equation into this form, I will clearly find that this is external derivative of some function. And this identity will tell me, whatever this form is closed, non-degenerate, this is Hamiltonian. And this can be checked elementary. So 2 omega dt. What I am doing, I'll take psi inverse L dot. So instead of delta L, I have to substitute what is derivative of L. Delta psi minus psi inverse delta L psi dot. And this brackets means I'll take trace and residue and sum of residues, this pairing. Okay, so what is it? Psi inverse L dot is a commutator of A, AL minus L, A, delta psi, minus psi inverse delta L, A psi, minus psi f. You remember the equation for psi dot was psi dot is A psi minus psi f, this function. That was the equation. So I use equations just to substitute it here. Sorry? It's not zero. It is supposed to be a dot. You see how you can contract two forms with a vector field. You plug in, so there was delta L, so I put L dot, the evaluation of derivative of L. The same, I had delta psi, so it is psi dot. I have half page of lines here. I don't know if I should reproduce all of them or leave it as a homework assignment. Actually, all what you need to do is just use the equation L psi equals psi k, that implies that delta L psi equal plus L delta psi equals psi delta k plus delta psi k. Using this equality, you just plug in, play a little bit. So I leave it as actually as a homework to verify that if you substitute it here, the only thing that would be left after numerical cancellation would be the term. Would be the term delta LA here. So you just play a little bit. This is what remains after this. But what is it? So this is the trace and sum of residues. It's sum of residues over residue over poles of L. Okay. This is two meromorphic expression. The sum of all residues is 0. So that equals, where are extra, so we're taking sum of over residues of poles of L. There is only one extra residue, which is pole of A. So it is equal to the residue at Z equals mu of the expression V Z minus mu delta L of mu. That is L K of mu, this is V, delta L K of mu, delta L. So it is 1 over K plus 1. Of course, there is a trace everywhere here. It's a delta of trace L to the power K plus 1 of mu. So what is Hamiltonian? Trace of a power of L at the point mu. It's just simple few lines computation that proves that your Lux equation is Hamiltonian, and actually this computation gives you expression for Hamiltonian. And that works for all known for me integrable systems, but believe it's more. It's for all. Actually, if you do the same computation, but with another simplex form I define, which is DLL inverse, after this result of computation, you will get L to the power K. So it's Hamiltonian with respect to another Hamiltonian, just you shift now ordering of Hamiltonians. So the proof that all equations are Hamiltonian are just straight line. What else? Okay, this is, of course you can, if you don't care about Hamiltonian theory, you don't do this exercise. But if someone asks you why the Hamiltonian, this is the answer. Is there anything else you can get out of this interpretation of Hamiltonian theory? So, Yes, and this again very important result that applicable more or less for all integrable systems. Let me just look once again at the definition. So action angle variables. Okay, let's look on omega once again. Minus 1/2. Here is sum over residues over poles of L, trace psi inverse delta L delta psi dz. Okay, if you compute this expression, probably I have no time to give a real computation, but just to explain what I mean, let's consider the case Lij, it's a matrix, which is depends on Z, and entries of the Z is elliptic functions. I'm looking on color because I can write this L for spin Algebraic-geometrical system, but I don't remember explicit formulas for spin case, but just for usual case. Pi delta ij plus sigma z plus xi minus xj sigma of z sigma of xi minus xj. This is, and this is 1 minus delta ij. So it's off diagonal terms of Lux matrix. There are simple modification of this formula for spin case, but let's forget. If you just plug in this L into this formula, do some computation, you will find that omega is just delta pi wedge delta xi, a result of non-trivial computation with elliptic function. And you may ask yourself, what's the purpose to define such a simple form in such elaborate representation? Is there any use of this? So there are simple formulas. In many cases, you can verify that KdV is Hamiltonian without using all these expressions. In particular, for example, for KdV, for Algebraic-geometrical system, this is very artificial way to write. Let's see, can we get something from this expression? Okay, first of all, let's look. We're taking sum of all poles over all poles of L. Why it's not 0? Because you should expect if you're taking a sum of residues at all poles, it is 0. Okay, where are extra poles of this expression? Why it's not 0? So if you compute residues as a sum of this expression at poles of L, you get some simple expression in terms of your original initial coordinate on your phase space. But then you use the fact that some of these residues are equal to residues to all the other residues. Where are other residues of your expression? They're at poles of psi. And you get, from this fact, you get that this omega can be written as delta z of gamma s wedge delta k of gamma s sum over all s from 1 to something. So gamma s, these are poles of your divisor. So you take the evaluation, the projection of your pole of your function onto z plane, and this is the Darboux coordinates for this system. This is how action angle variables can be explicitly found in all cases. And the transformation, you just use the fact that this is meromorphic form, so the sum of its all zero poles residues should be 0. Your initial form are defined as a sum of residues at poles of L. So that equals to that, the end of the story. Actually, this form is known now, okay, it first, without proving actually, it was suggested by Novikov and Veselov as it was called analytic Poisson brackets, as far as I remember. They observed that all Darboux coordinates for all known for that time systems can be written in such a form for two meromorphic differentials. Later, the same form is known now as a Seiberg-Witten form that appeared in n equals 2 supersymmetric theorems. But actually the proof, the ideology is this universal form and its expression. I'm almost ready to complete, but I would like to make looking. No, actually, I want to not to unify only the theory of integrable systems in a way that you use only a couple of letters. I also want to some extent, to unify the lectures given, at least today. So, actually, I want to show you some formula in a way that actually the same formula defines your symplectic structure on character variety. And as a formula on a character variety, it can be again explicitly computed. And it gives some non-natural, according to Kohler, two form on G cross G. Okay, let me just say a few words about.
You see the natural form, and not symplectic.
Again, this is no, you see, I don't know how to call this object, because in certain sense it's something natural you can write. From any reasonable point of view, it's very unnatural, because if you like, write it as a form on a space of operators, first of all, it is well defined only being restricted on some leaves. Only after restriction on these leaves it becomes closed, non-degenerate. As a form written in terms of L, it's neither closed, okay, it's senseless. But still, there are a lot of applications. So maybe better understanding is ahead of us, but I don't know. In the same way, I'm going, maybe if I can find, write a formula on G cross G to form that comes from this expression. Very unnatural, probably not closed, probably. But if you restrict it on a leaf, it becomes a Atiyah-Bot. So it coincides with any choice you made, Folk-Rossley or whatever. And you see, it is the same formula working for isospectral integrable system, for character variety for isomonodromy equation. There is no particular reason why it's so. Okay, so again, this is the definition of omega on the space of L's, space of operators. Let me just do the following. No. I'm just looking. So what? I have 15 minutes?
Yes, sir.
Okay. I said several times that there is no much difference between the example, my main example, I used all the time, and the Hitchin system. So why? And how you can look on a Hitchin system from the same point of view, space of operators. So suppose you have algebraic curve and a vector bundle over the curve. Vector bundle of rank R and degree VRG. Okay, so how one can think about vector bundle? Is there some natural coordinates on the space of vector bundles? One type of these coordinates was suggested by Turing many years ago, and it goes the following way. If you have a generic vector bundle of rank R and degree RG, then there exists a unique up to action of a linear group, collection of sections on V. So you can choose R section that gives you trivialization. So a generic point, this R section gives you trivialization of a fiber of this bundle. But because the degree is RG, so they cannot be everywhere linear independent. So they are linear dependent at certain points, gamma S. S runs from 1 to RG. So they become sigma sections. Alpha S sigma at the point gamma S, sum over alpha I from 1 to R is 0. So these sections become linear dependent at certain points. And the claim is that the collection of these points and these vectors at every point, they are defined up to multiplication by a scalar, are coordinates on an open set of vector bundles. They're called Turing coordinates. So generic point or open set in the modular space of vector bundles over gamma, is isomorphic to a symmetric product of RG copies of a curve, which is a point, and a vector in CP_R-1. So you can think about modular space just as a collection of points and the vectors. This is generalization when you think about line bundles over the curve in terms of divisor. So it's a matrix divisor, matrix generalization of a divisor, collection of points and a vector. And this is uniquely defines you a differential, a vector bundle. So, when you introduce this section, you can use to trivialize the vector bundle and write endomorphism of your vector bundle as just a usual matrix. Because in this trivialization, any endomorphism is just a matrix with a choice of basis. That's why Lux operators on gamma are matrices L L is a matrix valued function on gamma with poles at the divisor at a divisor D, which is a model of our points Zi in the example above. But in addition, with poles at points gamma S of the form Z minus Z of gamma S. So it has a pole alpha S, excuse me, beta S, alpha S transpose. So it's a matrix of rank 1. Alpha S is a vector, beta S is another vector. Plus LS0 plus O of Z minus Z gamma, Z of gamma S. I'm just writing the Lorentz expansion of L here. So, and the condition for this expansion is that LS 0 alpha S transposed equals kappa S alpha S transposed. So the matrix has a certain specific form here. Okay, and you can, and this is representation in the matrix form of sections H naught of and V tensor with canonical class. So it's really an explicit expression for points of Hitchin system. Now, you do the same computation as I said, you just plug in, and what you get for the form omega. Omega equals delta alpha S transpose delta beta S, sum over S. So omega becomes, alpha are coordinates on a modular space of vector bundles, beta are coordinates on in the fiber of cotangent bundle. So omega becomes a Hamiltonian canonical symplectic form on the cotangent bundle with through the modular space of vector bundles on the curve. Again, the same formula works for Calogero-Moser system, for KdV, for Kp, and serves for the Hitchin system as well. The same formula, just putting different understanding or different definition of L operator. Now, what you can, the remaining, what I wanted to say, we can use the same expression and consider flat connections on vector bundles on gamma. Actually, a flat connection on a vector bundle can be written in a unique way as one form of the has poles at gamma S of the form. It has the same form. Oh, sorry, I forget here to write one important condition for alpha transposed S, beta S, so scalar product equals 0. This is the Hitchin system. So L is one form having this expression, the same expression as before. The only difference is that alpha transposed S, beta S equals the scalar product. It was 0. So alpha is a point of the sphere. Orthogonal vector is tangent bundle, tangent vector. So the difference, the only difference when you're dealing with connection is that it's here. Should I put H? So this is H connection. So when you tend H to 0, so connections is H equals 1. When H tends to 0, it becomes a Hitchin system. So it's a family of H connections, and they have representation as just a usual matrix, one form on curve with a certain poles, structure of poles at these points. This is the condition, and L, and the rest, the remaining is the same here. Okay, the answer. You use the same formula with omega. You compute it on the space of L's. You get Atiyah bot symplectic form on a space of connection. So for so the details can be found in two of my papers. One is Lux zero curvature equation on algebraic curves, and the other isomonodromy equation. There are two papers where this connection with Hitchin system and also the limit of h equals to 0 is considered. Okay. My apology for the last part of my talks, because I tried to incorporate a lot of things but failed. So hope I did clear the initial message. Everything is very simple.
About the Turing parametrization.
Yes. Okay, let me just...
That has dimension R squared G.
R squared G, yes.
Yeah,
but then you should again, this is, I should... As I said, this choice of linear transformation of... Okay, this is parameterization of a framed bundle. So vector bundle with the choice of trivialization. Yes.
Okay, I think we'll be right. Thank you.